Here we're just re-teaching you from last year, like your summation notation, practicing that a little bit, working with some formulas, doing some limits, and really just doing areas of rectangles. That's really all this section is. We'll do the main definition of the integral for the next section, but just areas of rectangles right here. So summation notation, quick review. That just means you start here and you plug those numbers in for k, and you end it at 6, and you just plug in integers. So we'll plug in 3, we'll plug in 4, we'll plug in 5, and then we'll end it at 6. So if we plug into 3, you're going to have what? 3 times 1. That'll give us 3. And then you go plus, that's summation notation, your sigma notation, you add them up. So now we're gonna plug in 4. So we're gonna go 4 for that, 4 for that. So 4 minus 2 is 2, 2 times 4, that'll give us 8. And then we'll plug in 5, 5 minus 2 is 3, 3 times 5 will give us 15. And we'll plug in 6, that's our last number we'll plug in, 6 minus 2 is 4, 4 times 6, that'll give us 24. So just plug in integers for those k's, add up those numbers right there, and you're gonna get 50 for that answer. There's your summation notation. And then we'll give you a few not that great problems there, but we just give you a pattern and we have you come up with the sigma notation, come up with the summation notation. And so notice that whatever is not changing, you can use numbers for that. So that's just going to be like a 1 minus something over 4 squared. That's there on every single one of those problems, right? And then the only number that's changing is that number right there. It goes 1, 2, 3, 4. So I could put a k right there or an I right there or whatever variable you want to use there, and then you're starting it at the k equals 1, and you ended it at the 17. So there's your starting point, there's your ending point. And so we give you a few like that where you just say write the sigma notation, and there you just have to plug in numbers and add the stuff up. And then what we start to do, if we give you to the 15 or to the 150, you don't want to have to add up 150 numbers right there. So what we do is we give you these formulas, and these formulas will be more important in the next section when we do the general main definition of our integral. But the book might have i's in there, but we're gonna use it with k's. If you have a number, an I squared, or a k cubed, or an I cubed, or a number k squared, or k cubed, we're going to use these formulas here. So what you're allowed to do, if the summation notation has an I right here, you can rewrite this as 2 times the summation of I. So I just pull the 2 out. I'm doing the summation of this minus the summation of that. All right, and you can pull out the numbers. Your goal is to get a number, I, an I squared, or an I cubed. And then in the next section, we're going to switch to k's. It's going to be a number, a k squared, or a k cubed. And then what you're going to use are these formulas right here that we got. We're always going to give these to you. You don't have to memorize those, but if you want to take a second, jot those down, we're going to use them in the next section or the next assignment as well. But the summation for I, from I equals 1 to 15, this is your n. And so the formula is n plus 1 divided by 2. So I got that right there, all right? So if I use that formula, this is your n. So this 2 is already out there from our coefficient. And then I'm going to go n times n plus 1. So that's going to be 15. And then 15 plus 1 will give me 16. And then we're going to divide that by 2. So those 2's will cancel out. And then when you have a number, the summation of a number is a number times whatever the n is. So again, this is your n. So it's really like you're going 3 plus 3 plus 3 plus 3 15 times when you go from 1 to 15. So which means when you have the summation of a number, you're really just going to multiply those together. So it's just going to be 3 times 15 for that. And then what 16 times 15, that's going to be what, 240, I believe, minus the 45. So we'll get 195 for that number. So we give you a few problems where you're just really essentially just practicing those formulas a little bit, because we're going to be so important into that when we do our main definition of an integral. And then if you, instead of something like that, if you have something like this, distribute the I, and then you can do the summation of I cubed plus the summation of I, and then use your formulas. If you have something like this, don't make up your own stuff or get this from places you shouldn't be. Multiply that all out, make it look like that, and then you can do the summation of I squared plus 2 times the summation of I plus the summation of 1, and then use your few formulas off of that. These problems right here, when they look like this, these are ridiculously easy. I am not asking you to multiply all that stuff out. When you're approaching infinity, this only works, this shortcut, this trick only works when you're approaching infinity. All you care about is the highest degrees, because if you have infinity or a billion cubed, that's so much of a greater number than like just a billion, all right? So the highest degree is going to overtake the graph as you approach infinity. You already kind of know those ideas. That's what your horizontal asymptotes and your slant asymptotes are doing. But if you're going to say, when you see something like this, you're going to say, hey, if I were to multiply this all out, I have 64 times 2. So I have 128. And then you have n times n times n. So it's going to be 128 n cubed followed by a bunch of crap that you don't care about. All over, you have 6 times n cubed. And then you're going to use, and this is the limit as n approaches infinity. And then you're going to use that trick that you learned last year, where if your degrees are the same, it's going to be your leading coefficient. So my answer is going to be 128 over 6, which will reduce to the 64 over 3. If the degree on the top is larger, that answer is going to be infinity. If the degree on the bottom is larger, that answer is going to be 0. So there you go. So when we do the main definition of our integral, these problems are going to pop up in there, and we're already going to know how to do that. This is going to be the easiest part of the problem. You're going to take like just a few seconds there. So that's just some miscellaneous stuff in the middle, in the beginning of that section. And then what I want to do, I want to review a couple of problems with you, a couple of homework problems with you. There's all the work and all the answers for 2 examples there. And I just want to show you where I'm getting those numbers for a couple of them. And then the rest will be on your own. So what I'm going to show you is just finding the areas of rectangles. Now on the AP test, when we do our AP review, I already have some videos created where I explain the Riemann sum process. And those they use a left Riemann sum, right Riemann sum, midpoint Riemann sum. And I'll show you how to do all of that when the time is right, without any pictures whatsoever, without any plugging stuff in, and we'll be able to get a bunch of our answers looking at these patterns there. So I have those already created when we do our AP review. Right now, we just want you to find the areas of the rectangle. So if we look at this number 34 right here, and then what it's asking us is to find the areas of the upper bound and then the upper sum and lower sum. So the upper one might be a little bit difficult to see this, but what they want you to do for the upper areas is drawing rectangles. You're going from like 1 to 5, and you want to draw areas above the curve. And it just do base times height. So if I want to do this first rectangle, I'm going to go 1 times this height, which is 5. And then the second rectangle is above the curve here. You're looking at like this rectangle here. So it's going to be 1 for the base, 5 again for the height. And then the next rectangle, you can go right here. See how that whole rectangle is above the curve? And so you're going to go 1 for the base times it by 4. It's just length times width, base times height. And then the last one is going to be like 1 times 2 right there. And so I can add up each one of those areas. And then for, let's see if I can zoom in a little bit better. It's a little bit tough to see there, but just try drawing some rectangles, do base times height. When you do lower sum, they're asking for you to do the rectangles below the curve. So I can draw in a rectangle like here, and I'll do 1 times 4. Then a rectangle right here, I could do another 1 times 4. Then I could do a rectangle right here. See how this whole rectangle is below that curve? So I'm going to go 1 times 2. And then the last rectangle, this is above the curve. This one, it goes above and below. So the last rectangle isn't really there. It's just like with a height of 0. And so when you look at my answers for that number 34, I'm just doing base times height for stuff that's above the curve and below the curve, and getting the 16 and 10 answer right there. All right, and then I would want to do another even one here, but I'm actually going to do an actual homework problem with you just because it can show up on the paper a little bit better. This one's a little bit scrunched up and it's a little bit difficult to see. But see, on this one, these blue ones are the ones that are above. And so if you're not sure what the width of each one rectangle is, you're going from 0 to 1, and you see like 1, 2, 3, 4 sub-intervals there. You see 1, 2, 3, 4 sub-intervals. So what I'm going to do, I know that each increment is a quarter, so I could put like 0.25, 0.5, 0.75 right there, right? You know, it's like a quarter, 50 cents, 75 cents, and then your full dollar. So I can kind of put those widths in right there. And the thing is, so I know when I set up the areas of the rectangle, I'm going to take a fourth times a height, 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 because the bottoms are all going to be 1/4. And then, sorry, it's a little bit sketchy there, but so that's why instead of doing a fourth times a height, a fourth times a height, I'm just going to factor out a 1/4. I'm going to do 1/4 times all of those heights, just add it up. Instead of doing a fourth times that, a fourth times that, you could just write the 1/4 out there since it's equal width. And then here's the thing, when I do these blue rectangles, when I'm looking at this picture, when I want to get the height of this, so sometimes you could eyeball and say, hey, it looks like a half, but like right here, you're not sure exactly what the height's going to be. You don't need to guess when they give you the actual function. So look at this first blue rectangle right here. If I want to figure out the height, it's this point here. You got to use the point that's both on the curve and corresponds to the top of that rectangle that you're looking at right there, right? So like right there tells me to use x equals 0.25. So if I plug 0.25 in place for x, that'll tell me what that height is. So to get the area of this first rectangle, I go 1/4 times f of 0.25. I'll plug in the 1/4 right there and I'll get 1/2. Now when I go to the second blue rectangle, so this one right here, the width is 1/4. So I'm gonna take 1/4 times the height. Now when I do the height, I gotta go to this dot right here because notice this dot right here is both on the curve and it corresponds to the height of that rectangle. I don't use the 0.25 because when I go to the 0.25 at the top of that rectangle, it's out there in no man's land. So you gotta use this point here. That's x equals 0.5. If I take x equals 0.5 and plug it in place for x, that gives me my y value right there. That's on the curve, and that's the top. That's how high that rectangle is. So I take the 0.5 and I plug that in place for x. And then to get to this third rectangle, I use the 0.75, plugged in place for x, and you just move along that curve there, all right? And so that's why I use the 0.25 and then the 0.5 and then the 0.75 and then the 1 to get the areas of each one of those, to get the heights of each one of those rectangles. And I did the heights times it by the width, and it gives you the area right there. Now to get the lower, the purple ones, there's my work for that. So the purple ones, notice that there's only 3 of them. And so it's going to be 1/4 times the height, 1/4 times the height, 1/4 times the height. When I want to do the area of this first purple rectangle right here, I don't want to do anything over here. This is in no man's land. I got to use this point right there because that corresponds, it's on the curve, and it corresponds to the top of that rectangle. And I drop that down, that's x equals 0.25 right here. So to figure out how high this rectangle is, I got to take x equals 0.25, plug that in place for x. So that's f of 0.25 or f of 1/4. So when I did the f of 1/4, that gave me the height of that rectangle. I times it by 1/4. That gave me the area. And then when I want to do this area here, I got to use this point. That's the 0.5 or the 1/2 because that corresponds to this on the curve and to the top of that rectangle. And then for the last one, I use the 0.75 or the 3/4 because that's on the curve and it corresponds to the top of the rectangle. So you just take those x values, plug those in, that gives you your y value in the curve, which corresponds to the top of that rectangle. So there's all my work for that one. So there's an example for you there. Just do the best you can with those, but try to simplify that for yourself there if you're making it too complicated. Just you're doing areas of rectangles, just length times width. The only difference is you got to take x values and plug those into the function to figure out how high up you're going, and that's going to give you your height. And then that's a little bit weird sometimes to do the areas of rectangles. Students have told me they don't particularly like doing that, even though it's just easy stuff there, just easy arithmetic there. Sometimes they don't like doing that. They tend to like the main definition of the integral a lot better when we do that in the very next video right there. Even though it's a little more intense, they just like that better there. They use the exact definition there. But there won't be any confusion on the AP test with what's above, what's below on certain problems right there, because they'll be clear. Use a left, right, or midpoint Riemann sum. And like I said, I'll have the videos explaining already how to do those. And we could even do those without even looking at the picture. So that'd be a little bit more powerful in the future. So whenever we get a chance, I'll show you the Riemann sum stuff there. But I just want you to get into your head when you see Riemann sum on the AP test, you're really just doing areas of rectangles right there.